Hello, today in this video the goal is to explain how Transaction Analyzer is computing what we are calling the summary of delays. So basically this is the screen when you want to have a breakdown for the various delays computed by Transaction Analyzer for a given transaction. So to understand how it is computing the time due to the latency, bandwidth, protocol, congestion, and the tier processing. Before looking at the tool, I will use a few slides to help to understand the concepts here we are using. About the delays for a given transaction, we can have three categories. The first one, processing delays on the client or the server. On the client, we will talk about the user think time. In that case, this is the time where the client is waiting or doing something before submitting a request. It can be using the keyboard to type something, using the mouse before clicking OK, whatever. And we are calling that the user think time. For the server delay, it will be the processing delay. So the server is receiving a request and it needs to do some work before starting to answer. It will be the server processing delay, or it can be also all the delay related to the server talking to other tiers when we are not capturing all the traffic. So for example, it can be an application server that needs to connect to a DB server to get the data before starting to answer. If we are capturing only on the client, we will not be able to understand that the server is trying to connect to the DB server. If we were capturing on the server, we will see this information and we will see also the communication between the application server and the DB server. So this is for the processing delays. About the network delays, we have various categories. Protocol, which is usually related to TCP behavior. Bandwidth, which means the time needed to send the data on the wire. Latency, in that case, it means the propagation delay. It will be the time for 1 bit of a packet to go from the client to the server. This is why we are saying it is governed by the speed of the light. Congestion, also known as queuing delay, it could be related to intermediate devices like routers, firewalls, load balancers that can queue the packets before forwarding them to the destination. And also packet loss that will be related to TCP here, because if we are using UDP, we are not dealing with packet loss, but with TCP, it will be up to this protocol to retransmit the packets that have been lost, and the delays related to packet loss will be included in the protocol delay, because it is the protocol, it is TCP that is dealing with that. And finally, we have also application related delays. We are talking about code inefficiencies and chatty applications. We will talk about that. This is when there is a lot of application turns between the client and the server. So instead of asking for a lot of data in one request, we will say that the client sometimes can ask many requests and is waiting for each request to come back before asking for the next one. So when we are using a transaction analyzer to analyze a transaction between a client and a server, the network can be very complex between each tier. Now, for transaction analyzer, it will emulate the whole network as a big pipe, as we can see here at the bottom, using three parameters: the bandwidth, the latency, and transaction analyzer is using the one-way latency, so only in one direction, so it is half the ping value, we can say, and the congestion. And when we are importing a trace, transaction analyzer is able to identify the one-way latency. Usually it means it is looking at the TCP three-way uncheck. It will be also able to understand when we have some congestion, but there is one parameter that needs to be checked and often changed, which is the minimum bandwidth. Basically, this is the weakest link between the client and the server, and it is usually the one access link on the client side. This value is not found by transaction analyzer. This is something you need to add to provide accurate results. If you are not doing that, the results can be wrong. We will see that in the demonstration a bit later. So as we can see here on this slide, when the packet is leaving the source, we can have three categories: the bandwidth delay, which is the time to insert the bits on the link, and this is also called the serialization delay. Then we have a latency delay, which is also called the propagation delay. Again, this is the time for the first bit of a packet to reach the destination. And we can have congestion delay when I am not the only one using the link between the client and the server. And for a protocol, again, this is mainly related to TCP protocol here, because we can have sometimes some behavior of TCP that can add some delay for a transaction. And as said before, the packet loss is handled by the protocol, again, TCP here. So if we are using a simple example, here we have a file size of 30 megabits. The bandwidth is 1 megabits per second. And here we can see that it took 50 seconds to send the whole file. In green, we have a bandwidth delay, 30 seconds. The simple math here is easy to do. Since I have 1 megabits per second, 30 megabits, it will take me 30 seconds to send all the packets to the destination. We have a very large latency delay here. It is an example, 5 seconds. We can see that in red. It is only one time, and it is for the first bit to reach the destination. And in this example, the total delay was 50 seconds, so it means that it is not 35, and the remaining 15 seconds are related to queuing delays. Again, this is an example here, just to clearly understand how transaction analyzer will try to find this information. There is no client processing delay, user think time, server delay here. We are only looking at this simple transfer, and we are not including TCP here, because we can have also some delay added by TCP when the sender is waiting for acknowledgements to come back from the receiver. So here we are looking at what we are calling in transaction analyzer the application chart for messages. So we can see that we have removed the TCP acknowledgements that are usually in red red means no payload in the packet or the message. So what can we found just by looking graphically at the application chart? So we are talking about messages, and these messages can have one or more packets associated with them. The color of each message, each arrow, is depending of the payload, the amount of bytes for each application message. Here we are adding the processing delays. So on the server, usually the server is at the bottom and the client on the top. So here we have some server processing delay. We have also some client delay before sending the next request, etc., etc. So what Transaction Analyzer will do, it will sum each triangle here to compute the total processing delay at the client and at the server side. Another concept that is important is application turns. So this is when we have some data that will go on the other direction. So here we can see that we have one application turn, a second one, third one, fourth, fifth. Here it is always sending data in the same direction, so there is no turn. There is the sixth one here and the seventh one here. So 7 application turns here. And what is important to understand is that each time there is an application turn, we need to wait for the first bits of the packet to reach the destination. Again, this is related to the latency. And when we are talking about chatty application, it is when we have a lot of application turns. And we need to wait for the first bits to reach this destination. And if the latency is high, it can add a lot of delay for the total response time. So here, question is, how long does it take to serialize this packet on the onto the wire? So basically, this is the transmission delay. So it is based on the bandwidth and the packet size. So we are not talking about latency here. So the slope of the arrow will depend about the size of a packet or the size of a message and the bandwidth. If the bandwidth is very high, it will take less time to transmit the packet. And the formula, sorry, is the packet size divided by the bandwidth, not as I said before. About packet loss, it depends if the capture has been done on the client and on the server, or only on one direction, on one of them. So if the capture has been done on the client and the server, we can merge the two traces together, and in that case it is easy for Transaction Analyzer to see that, for example, here this packet has been sent, but it has not been received on the receiver, and it will mark that as a dropped packet. If we are capturing only, let's say, on the server at the bottom, and we are looking here at these two identical packets, Transaction Analyzer will understand that there is a retransmission because we can see twice the same packet. By the way, this is why it is better, if you can choose, to capture on the tier that is sending the traffic. Why? Because here, for this example, Transaction Analyzer will understand that the packet has been lost because it will see the two identical packets leaving the server. But on the other side, since the packet has been lost somewhere in the middle, it will only see the retransmitted packet and not the original one, because it has been dropped before. And it will be flagged as a TCP out of sequence packet. meaning it is a potential retransmission, but we are not sure. So there is a difference here if I am capturing on the server or on the client when looking for this kind of retransmission. Something important to note as well. And a few words about the protocol delay. So we can see here, for example, there is a packet or message being sent, but there is this purple triangle here, meaning that TCP must wait for acknowledgement. They are not shown here again. To receive, it needs to receive the acknowledgement before sending the next set of packets or the next message. So this is related to the TCP window size. That can be sometimes a bottleneck. And about congestion, transaction analyzer will try to compute the ideal time to transmit a packet using the dotted arrow here. But in this example, the real time to transmit it is here. So there is a delta time here between the perfect time, the ideal time to transmit the packet, and the real one. In that case, the difference will be computed as queuing and congestion delay, because there is a device in between that is adding some delay by queuing packets before forwarding them. So these are the various delays transaction analyzer will compute automatically for you when analyzing a trace. So now I am switching to a real example. The same one as used for at the beginning of the video when I was showing you the summary of delays. So this is this transaction here. Again, we have this is the data XN chart, and we have two views, the application view and the network view, and I can show both of them. It is important to understand the difference between each of them. Before doing that, I am going to the tree view to get some information about the transfer itself. It is a file transfer, and here, like in the data XN chart, I have two ways of viewing the data, looking at network packets or application transactions. If I am looking at network packets, it will show me each individual packet as they have been sent on the wire. And I can look at the decode here if I want. So here, and here we can see, and for each packet we can see the amount of application payload sent in both directions. And so we have a lot of them, and we can see sometimes here the acknowledgement because there is no payload, and here, for example, there is a part of a file that is requested by the client, and we can see the answer sent by the server and the acknowledgement, and so on. Alright. If I am switching to the application view, here we are talking about application messages. It means that from the packets themselves, transaction analyzer will try to understand which application messages are sent by the client. So here we can see it is getting some information about the file. We can see the name of the file. And if I am looking here to this kind of application message, it is a pretty big one with a small request from the client and about 60k bytes returned by the server. If I am expanding this one, all I will say is the request and the answer, and the size of the answer. So this is how a transfer is done. When it is started, it will ask and get the file using this chunk of data. We can see them here again. Look at the application payload size. Orange is between 1 to 100. Remember the 63 bytes here. This is one of them. And then there is an answer. And here we can see that we have 43 packets for this answer, for a total payload of 61 kilobytes. So what I can do here, I can select both of them and exclude others. I will zoom. And what we can see here is the difference between the application view and the network view. We have the same thing here for the request from the client. Why? Because the size of a payload is enough to be carried using a single TCP segment. So this is why I am also finding the same information at the bottom. But for the response is pretty big. It is 61 kilobytes. TCP cannot send that in using a single TCP segment, so it will send multiple packets, each of them with a length of 1460 bytes. And we can see the TCP acknowledgement. Usually it is 1 every 2 TCP segments. And what is doing Transaction Analyzer is to reconstruct the application message from the network view. And this is what will be used to compute the application, the summary of delays. It is not based on the network packets, it is based on the application shards. So now I will include again all packets messages, doing a full zoom. I can only stay with the application chart now, and when I am looking at the summary of delays, what could we see here? About the processing delays, there is almost nothing here. The yellow part is very small. Why? Because there is almost no processing delay. If I am clicking here on Show Dependencies, it will add some triangle. Purple for network delay, white application delay, and user think time. Here there is nothing like that. Here, if I am trying to look at the application delays, I need to zoom. And here I can see, for example, when a request is arriving at the server, I can here see that it is taking less than 1 millisecond before starting to answer. So it is answering pretty fast. And this is why we have almost no tier processing delays here. The majority of the delay is due to latency, and before looking at that, it is important to check the how we have modeled the network between the client and the server. So there is a one-way latency of 45.6 milliseconds. Once again, it is the one-way latency from the client to the server, or the server to the client. It is the same value used in both directions. And we have a minimum bandwidth set to 10 megabits per second. Once again, this is not the default value. If I was importing the trace from scratch, it will use 1 gig. And I need to change this value to match the real one, which is in that case 10 meg. So as we have seen, we have very few processing delays. The latency in red is taking most of the time here for the transaction. And what it means, if I am double clicking here on the red part, I will use and show the application turns chart. So this is the number of application turns per second between the client and the server. And because the Y-way latency is a bit high here, it is 35 milliseconds, each time I am doing an application turn, it will take 45 milliseconds for the first bit of a packet to reach the destination. So this is what we can call the shutty application here, because most of the delay is related to latency. And this is a file transfer, and we know that it is not very good to do that on the WAN. On a LAN, it would be good because the one-way latency is almost zero. And we will almost not get any latency delay, but on the WAN, we can see the impact right away. About the other results, bandwidth in green. So this is the time to transmit the bits on the media. And we have also some congestion delay, some queuing delay. And here there is no protocol delay at all due to TCP. That means there is no packet being lost. For example, if I am looking in the statistics about the transmission and so on. So this was a short video to explain how a transaction analyzer is computing the summary of delays. A last example here that can be useful is the prediction. So what I can use what we are calling quick predict to try to estimate what will be the response time for various network conditions. So for example here I will add a scenario using network at time of capture. That means it will use the input for the minimum bandwidth, 10 megabits per second, and the latency. And here we can see we have a lot of red. Let's say I was able to change the latency. I cannot do that because it is based on the geographical location between the client and the server. Or I can use one acceleration, for example. It is another possibility. But let's say I cannot do that. If I am going down to 4 milliseconds, we can see here that the impact due to the latency is smaller. And if I was using 1 millisecond, the response time will be mostly related to the bandwidth, which is 10 meg. So I will add again the value used for the real trace. Response time is about 10 seconds. It is a bit more, it is 12 seconds here. But remember, what is missing here is the congestion delay. If I want to model that, I need to use the link utilization. So let's say I am saying that the link was used at 50%. I am almost reaching, and here it is a prediction, the real response time. Here it is a bit more than 12 seconds. And if I'm looking at the summary of delays, it is 12.1. And this is matching, this is the reality, and this is the prediction. So this is very useful, this feature, a quick predict chart, to try to estimate what could be the response time for various network conditions. Could be various remote sites with not using the same bandwidth and latency. So this concludes this presentation about transaction analyzer and how it is computing the summary of delays. I hope you enjoyed it. Thank you. Bye bye.